a walking bipedal robot from scratch named Xuanwu. I'll show you in this video how robots now seen everywhere learn to walk and share some insights from my journey. Although this project's technical difficulty is quite high, I promise you this isn't a technical video, but rather an interesting story. Without further ado, let's begin. A year ago, I just started grad school in robotics, watching impressive demos one after another coming out continuously. I wondered if I could build one too. I really liked the frame robot from The Wandering Earth 2. Its design was really cool, so I wanted to create one based on that, but the robots we commonly see today don't look like that for good reason. After 3D printing my first prototype, I discovered the center was too far from the foot supports, requiring too wide a stance to balance. Simply put, the stride was too wide to walk. Try standing with feet apart and squatting slightly. See how difficult walking becomes. So unfortunately, my frame robot idea died before it could develop. After that, I optimized several versions, but 3D printed plastic parts weren't strong enough. The machine kept breaking. So all that exploration was basically wasted effort. Fast forward to this summer, I completely redesigned the robot, switching to aluminum alloy structure and installing more powerful motors with clever mechanical design improvements like these joint positions based on human physiological movement ranges. This protects the robot and makes wiring easier. More importantly, it protects me. During testing, if it malfunctions, the thigh won't spin 360 degrees and kick me across the room. After designing, next came manufacturing. All parts were made with Global Manufacturing's 6-axis milling. This isn't an ad. The price was just too good. I want to promote them. If Global Manufacturing sees this, they can contact me about ad fees. For motors, I use Damiao 4310 and 4340. This is an ad, thanks to Mr. For the 80% discount, Damiao motors are good and durable. I made a simple rendering to show you a walking robot like this, what essential parts it has to make the robot move. The most important part is the motor using 12 motors from bottom to top, 2 degrees of freedom for each ankle joint, 1 for knee joints and 3 for hip joints. The waist carries other components. A battery provides power, a high-performance edge, computing platform, a small computer handles calculations, and IMU provides angle data, angular velocity, acceleration, etc. A remote relay to cut power remotely when needed, preventing harm. If control is lost, these parts make up the Xuanwu robot once all parts arrived. I unpacked them. You can see the assembled robot looks pretty cool. I'm sure someone in the comments will say, cool? Ordinary to me. Indeed, my design skills are limited. I can improve structure and appearance in the future. Now that it's built, it needs to walk the most mainstream method currently used by almost all robot manufacturers in their demonstration videos, whether XPeng's Catwalk or Boston Dynamics Marathon or Unitree's Off-Road Running, all use the same basic implementation, that is, reinforcement learning. The name sounds intimidating. I was confused at first with terms like Q-learning, Bellman equations, etc. But it's like dog training. Yes, you heard right. After complex theory, robots walking, jumping and flipping is essentially similar to dog training. Let me use my Xuanwu robot as an example. Let's look directly at the process, more intuitive than my verbal explanation first. We need a robot. Just having the physical robot isn't enough. We need a digital version too, with nearly identical physical properties. Then we put it in a simulation platform, which is a virtual real-world environment, can somewhat accurately replicate robot movement and physical collisions. The next step is training. Training needs a purpose, like teaching a dog to sit. The same applies to robot walking. The goal is usually to move at a specified speed. With a goal, proper guidance is needed in walking when robots move in simulation. Moving at the target speed earns rewards. There are also penalties to prevent jerky movements or speeds too high for motors to execute, or learning strange movements like limping while walking. jumping or flying instead of walking. To speed up this learning process, GPUs are used for parallel training. Thousands of robots train together. Good ones get carrots, bad ones get sticks. But simulation is just simulation. It differs from our physical world. Joints may wear out circuits, sensors may lag or vibrate. Floor friction is complex. The solution is actually simple. We add these uncertainties to simulation. This method is called domain randomization. Each robot faces different challenges. One robot might have inaccurate joint feedback. Another might face slippery ground. When robots adapt to imperfect simulations, they can handle the real world better. Many robots learn through repeated failures, gradually improving their walking. After compiling all this experience, they develop a complete strategy. This is called an end-to-end strategy. Usually it's a neural network or a complex function, simply put, applied to humanoid robot walking. It works roughly like this. We collect instructions, target speeds, plus physical data from sensors, like foot speed and direction, joint positions and velocities, plus the previous function output. These values enter the neural network. Think of it as a black box, producing target positions for each joint. And this whole process is called strategic reasoning. Repeating this process at every moment, the robot can now follow your instructions. It's truly amazing. Of course, such a broad overview necessarily ignores many important technical details, but the core understanding is basically this. If you understand the process described above, many questions actually solve themselves. For example, many people say robots are remote controlled, but we use remotes to control forward and backward movement, left, right, turning left and right. This corresponds to just 3 speed values. How these values become joint instructions is what we discussed earlier. And with these 3 speed command interfaces, I believe you can understand the remote is just one way to provide speed commands. Many mature technologies, like simultaneous localization and mapping, SLAM, and the path planning based on it are actually core to cleaning robots or hotel service robots. Knowing their location and planning paths independently, they can operate without remotes by issuing speed commands to reach desired destinations. So next time someone says remotes aren't sophisticated, you can smile slightly without a hint of contempt. Tell them remotes are just command carriers. The challenge is mapping commands to physical movement. Unfortunately, from simulation to reality. Even with methods like pre-randomization, it's not always smooth sailing. I debugged continuously for nearly 2 months. To achieve these decent results you see now, during this time, the robot fell and broke often. When it finally took stable steps, the feeling of achievement it gave me was beyond words. Bipedal. Walking can be traced back to the Sahelanthropus from 7 million years ago. People take walking on 2 legs completely for granted. But teaching robots stable walking is a path full of challenges. Since the 1970s, from passive walking based on gravity and inertia to simplified model-based footstep planning to optimization-based predictive and whole-body control up to today's reinforcement learning. Sometimes I feel like we're a group of modern-day Prometheus, except we're not stealing fire, but the divine spark of movement itself, trying to ignite it in cold machinery. There are many reasons to give up in this process, but when I saw it finally take stable steps, all the late-night debugging and refinement suddenly made sense. It's an incomparable joy of creation, like a parent's delight seeing their child walk, and an engineer's satisfaction in advancing the world. One small step. Technology evolves, methods become outdated, but this primal emotion born from creation will always be the warmest light guiding us forward.